Hey guys, welcome to Safi Mixed. In this video, I want to find the equations of motion of Atwood's machine placed inside an accelerated chamber. I have already solved the problem of Atwood's machine, of stationary Atwood's machine, but here we consider a little different scenario. That is, I consider a chamber like this. And inside the chamber, I fix a pulley and I pass a thread over it and I connect a mesh M1 to this end and mesh M2 to this end. Obviously, there is tension and I call this T1 and this one I call T2. Then the weight of this mesh is M1G acting in the downward direction and of this one is M2G. Now, the whole chamber is moving with certain acceleration, and let me call the acceleration alpha in the upward direction. When this is the scenario, then obviously we cannot observe the dynamics or the motion or acceleration of the masses or of Atwood's machine from within the box because it contains acceleration, and this acceleration would create fictitious forces. So what we do, we want to solve this whole problem along with the box from the reference of an inertial observer. That is, we want to analyze the problem from the ground. And for that, I want to fix the distances. I consider this distance, the distance from the floor of meson 1 to be x1, and the distance of the bottom of the chamber of mesh 2 to be x2. The distance of the chamber from the ground, let me write that as x. Then the distance of the mesh from the ground, I write that as x1 prime. Remember, x1 prime. Don't confuse the prime with derivative. It is just a representation. And similarly, the distance of the second mesh from the ground, I represent with x2 prime. Then, in order to observe the motion with respect to an observer standing on the ground, which is inertial observer, I need to link these distances with each other. And from the diagram, I see that x1 prime is in fact equal to x plus x1. So I can write x1 prime equals x1 plus x, and let me call this equation 1. And similarly, from this geometry, I see that x2 prime equals x plus x2. So I write that as x2 prime equals x2 plus x, and I call this equation 2. Now, when the whole system is moving, the pulley is rotating, T1 and T2 are in motion within the chamber, and the chamber is accelerating, then all these three distances are changing simultaneously. That is, this distance is changing, this is changing, and this is changing, because if it is moving in the upward direction, this distance will change, and if the block is moving, this one block is moving either in the upward direction or downward direction, this one distance is changing, and obviously with the change of this distance is also changing. So I can differentiate these two equations twice with respect to time to write equations for accelerations, and that I can do if I differentiate this equation twice. I just put for the differentiation with respect to time dots. So x double dot 1 prime is in fact equal to, according to that equation, x double dot sub 1 plus x double dot. I get that from equation 1, so I call this equation 3. And from equation 2, if I differentiate it twice with respect to time, I can write x2 prime and put in double dot equals x2 with double dot plus x with double dot. Now I call this equation 4. Now you can recognize that the double derivative of this distance is in fact the acceleration of the whole frame, which we set equal to alpha. So I can write x double dot in terms of alpha. And x double dot 1 is in fact the acceleration of this mass with respect to this bottom. So this is the acceleration with respect to the change in this distance. And similarly, x2 double dot is the acceleration of m2 with respect to the bottom, which is the change, the derivative, the double derivative of this distance, x2. So we can recognize x double dot is alpha, and x double dot 1 as the acceleration of mass m1, and x double dot 2 as the acceleration of mass m2. Now, we put a condition. I'll implement that condition later on, but now we want to write the Newton's second law for each mass separately with respect to this observer. According to this observer, the net force acting on this mass is in fact, if I consider the downward direction positive, then I can write m1g minus t1 equals f net 1. Let me call this 1. And this in turn would be equal to m1 x double dot prime 1, because that is the acceleration of the mass with respect to this observer. And similarly, for this one mass, this observer, the observer at the ground sees the equation to be m2g minus t2. The extension equals f net 2, and that would obviously with respect to this observer is equal to m2 x double dot prime 2. So I call this equation 5 and this equation 6. Now I can even remove the net for, but okay, but let it be the way it is. Now, if I substitute the value of x double dot 1 from equation 3 into equation 5, I can write this equation in what is the whole equation. I can write this as m1 into, for x double dot 1, I write this value, x double dot 1 plus x double dot equals m1g minus t1. And we are interested to find this acceleration, x double dot 1. So I can write m1 x double dot 1, and I'm taking this term to that side and writing the equation m1g minus t1 minus m1 x double dot. Okay, I call this equation 7. And from equation 6, using the value from equation 4 for x double dot prime, I can write that as m2 into, putting this value, x double dot 2 plus x double dot equals m2g minus t2. And again, I'm interested in finding the acceleration of the second particle, x double dot 2, so I can take this term to the right of the equation and can put the equation into this form, m2 x double dot 2 equals m2g minus t2 minus m2 x double dot. I call this equation 8. Now, we want to solve equation 7 and 8 for finding the acceleration of masses, that is x double dot 1 and x double dot 2. But there we want to make two assumptions. Number one, we say that the string is inextensible. When the string is inextensible, then obviously the distance at this side covered by matching 2 would exactly be equal to the distance covered at this side, and the acceleration at either side, or the acceleration of the two masses, must be equal in magnitude, but that must be opposite in direction. For example, if this mass is moving in the upward direction, then this mass must be moving in the downward direction. And similarly, if this is moving in the upward direction, this one will be moving in the downward direction. There is a change, a difference, or the two accelerations are opposite. One is upward and the other is downward. Therefore, I can write a relation between these two in the form that x double dot 1 is always opposite in direction and equal in magnitude to x double dot 2. That is, this acceleration is equal to this acceleration in magnitude but opposite in direction. So I'll use this condition, and the second condition I consider here is that the string is massless and there is no friction in any part of the pulley. So when that's the case, if there is no friction, then this tension should always be equal to that tension. That is, the second assumption that we make is that, or the second constraint that we put on our system, is that T1 equals T2, and I set both of them equal to T. So under this condition, I now add equation 7 and 8, and if I add equation 7 and 8, I can write them as, the result I can write m x double dot 1 plus m, no, I subtract, because I want to eliminate T1 and T2, therefore I subtract equation 8 from equation 7. So I put a minus sign over here, that m2 x2 double dot equals m1g minus, I replace T1 with T, so I put T, and then minus m2g, and I'm subtracting this, so this would become plus T, in the last term would become plus m2 x double dot. Here I missed one term, no, this one, I'm subtracting this, so here should be, at this position, we should have minus m1 x double dot, that must be here. So now I can set x double dot 2 minus x double dot 2 equals x double dot 1, because minus double dot 2 is equal to x1, and write this side as m1 x double dot 1 plus m2 x double dot 1 equals, and I can cancel on this side this t with this t, and can take g common from these two terms, and can write this as m1 minus m2 g, and from this term and this term I can take minus x dot common, so it will become minus x dot, or I write this like this, m1 minus m2 into x double dot. And now from these two terms, from this side, I can take x double dot common to write this as m1 plus m2 into x double dot 1 equals, and from these two terms, I can take m1 minus m2 common to write it as m1 minus m2 into g minus x double dot. So I can remove which one equation that I don't need these equation anymore, so I remove them from here, and from this equation I can write x double dot 1 equals m1 minus m2 divided by m1 plus m2, the whole multiplied with g minus x double dot, and x double dot is the acceleration alpha, so I write that is alpha. So this equation, and I can replace this with acceleration a. So the acceleration of particle 1 is given by this thing, and according to this condition, the acceleration of particle 2 or mass 2 is the negative of this thing. So we find the acceleration, and substituting the value of acceleration in either this one equation or this one equation, I can fix the value of t with, because t1 is equal to t2, so I can put the value of a to find tension T in the string in terms of the known quantities. One thing more you must note over here. Now, if alpha is 0, that is, there is no acceleration in the chamber, then this relation is exactly the one we obtained for the stationary Atwood's machine. So the effect of acceleration is there. And now, if the particle is moving in the downward direction, then this sign would reverse. It would become plus. So that's the only difference. When the chamber is moving up or down, we can use those information there. Okay, now now I can find the velocity, since if you look at the acceleration, now all these are constant quantities, masses, the g and alpha are constant, so I can write acceleration as a constant c. And the acceleration at any time can be written as the derivative of velocity, so I can write dv over dt equals c, or from this I can write dv equals c dt. And if I know about the initial velocity, I can find the final velocity by integrating this equation, and that is now straightforward. I can integrate this equation from v naught to vt dv equals, since c is a constant, therefore I write this as a t is equal to 0 to t dt. And I can rub these things out now. And from this I get v from v naught to vt equals c times t from 0 to t. And if I put the limits, I write vt minus v naught equals ct, because for 0 it is 0. And from this I can write vt equals v naught plus ct. And you see, again, this is the equation of a straight line on velocity time plot, where v naught is the initial velocity and gives the intercept on the v-axis. That is, if I plot this equation on a vt plane, it looks like this, where this is the value of v naught, and the slope of this line is equal to c. That is, we have delta t and delta v equals delta v over delta t, which is constant acceleration. And similarly, I can find the positions of the particles if I want to write vt in terms of the position dx over dt equals v naught plus ct, and taking dt to this side by using separation of variables, I can write this as v naught dt plus ct dt. And again, using the initial conditions for position, that is at time t naught equal to 0, x is x naught, I can integrate this equation from x naught to xt dx equals v naught. I'm taking this out of the integral because this is constant, so I write dt from 0 to t, and again c is constant, I can take that out of the integral to write it t from 0 to t dt. And I can put a prime to differentiate between the limit and instantaneous time, so I'll put a prime over here, and these are different, so it is not needed to put that over here. So the result of this integral is x with limit x naught to xt, and this is equal to v and v naught, and that is t from 0 to t, and this gives me plus half sorry, c divided by 2 into t from 0 to t. And if I put the limits, I can write x minus x of t minus x naught equals v naught t, the 0 goes to 0, plus half c, oh, this is in fact t squared. I missed the t squared, so it is half t squared. And you see, this is again, if I write xt in terms of the initial condition, it goes to x naught plus v naught t plus half c t squared. And this is obviously the equation of a parabola, so which is obviously similar to the equation of motion under constant force, because c is the constant, acceleration, as we saw previously, it depends on masses, on alpha, and on gravity. So this way we can find the equations of motion for Atwood's machine placed inside an accelerated chamber. And thanks for watching.